This video is about the attention mechanism. Assume we have a set of objects, each of them having a particular shape and color. We are then given some shape and our goal is to find the color of the object with the most similar shape. To compare the similarity of the shapes, we define a vector that describes that shape. We also define a vector for each item that holds the value we are interested in, namely the color. We can then evaluate the similarity of two vectors. In this case, the rectangle and the square are very similar, and the ellipse is also slightly similar, as its general shape is not too far off from the rectangle. To now actually find the color of the object that has the most similar shape to the rectangle, we combine all colors by weighing them by the similarity. We now add up the colors to compute our final result, a dark blue. This toy example summarizes the main concepts of the attention mechanism. More formally, we are given a query vector q and n input vectors xi. In the example before, the query q was the rectangle, except here it is already in the form of a vector. The input vectors xi were represented by the different shapes. Using matrices wk and wv, we compute the key vector ki and the value vector vi for each input xi. In the example before, the key vector captured the type of shape while the value vector captured the color. The attention score Si is then calculated as the dot product between the query q and the key vector ki. We finally use softmax to add up all corresponding value vectors to produce the attention output y. The dot product can be understood as a measure of similarity. If q and ki are similar to each other, the attention score will be large. It also leads to the name of this particular type of attention: dot product attention. Other variants using different similarity measures exist too. Let's look at a numerical example. Consider that we want to find in what position a sequence of 5 integers contains the value 3. We use a ReLU to create the keys ki and a one-hot encoding for the values vi. We can now compute ki and vi for every input xi. For q we are given the vector -1 -1. We then compute the dot product between q and every key vector ki, which gives us our attention scores si. Plugging the scores and values into the softmax finally gives us our result vector y. As you can see, y contains its biggest value at the position of the 3 in the original sequence. Due to the softmax, the output is not quite as clean as one might hope. This is due to the 4 in the input being slightly similar to a 3 for our chosen similarity measure and keys. Attention makes use of weight sharing by applying the same matrices wk and wv to every input xi. It therefore can process inputs of any size. All operations in the attention mechanism are differentiable. This means that we are able to train our weight matrices wk and wv using backpropagation. In practice, a neural network might consist of multiple attention aggregations in parallel, called multi-head attention, or in sequence. The queries might also be directly computed from the inputs. This would be called self-attention. A combination of these techniques is strongly used in the transformer architecture, the current state of the art in natural language processing. This concludes the attention mechanism. Thanks for watching this video.